And again, I will make this recording and all recordings available for you on Canvas here. So, all right, so section R5 is entitled Factoring Polynomials. And factoring polynomials is a survival skill, not only for this course, but for any other math course you take beyond this. You get into trigonometry, pre-calculus, calculus, differential equations, et cetera, no matter how high you go in mathematics, you always have to know how to factor polynomials. That's always something that comes back to haunt you. So I'm going to address that, and hopefully most of this is review in section R5. The first thing that we normally run into in elementary or intermediate algebra in factoring polynomials is factoring out what is called the greatest common factor out of all the terms of a polynomial. So that's normally the first thing that we have to concern ourselves with here. So like if I give ourselves this polynomial here, it has 3 terms in it. So technically it's called a trinomial. How could we factor this trinomial? Well, I'm trying to find what's called the greatest common factor or greatest common divisor of each of these 3 terms here. Now, if you look at just the coefficients, 15, 30, and 5, what would be the largest number that divides into 15, 30, and 5? Anybody?
5.
5. Okay, so 5 definitely would be the greatest common factor of 5, 15, and 30. As far as the variable c is concerned, ironically, it seems like a paradox, but since we're trying to find the greatest common factor of c that can be factored out of c to the 5th, c to the 4th, and c cubed, we factor out the smallest exponent, actually, ladies and gentlemen. So we can only factor c cubed out of all 3 of these terms. And as it turns out, that would be a greatest common factor that we can factor out of all 3 terms. So on the next line of my paper, I'm going to put an equal sign. I'm going to then acknowledge my greatest common factor that I'm going to factor out of all 3 terms, times, and then I'm going to put a set of parentheses here. And now I need to ask myself, what do I leave behind inside the parentheses after I factor 5c cubed out of all these terms? Well, when I factor 5c to the 3rd power out of the 15c to the 5th, what am I going to leave behind? Ask yourself, 5 has to be multiplied by what to give you back 15? That would be 3. C to the 3rd power has to be multiplied by how many more c's to give you back c to the 5th power? That would be 2 more factors of c. Does that make sense? I would leave behind 3c squared after factoring 5c cubed out of the first term. Minus, when I factor 5 out of 30, what do I leave behind? I would leave behind 6. When I factor c to the 3rd power out of c to the 4th power, how many c's would I leave behind? Well, just 1 c would be left behind because c cubed times c gives you back c to the 4th. Plus, when I factor 5c to the 3rd power out of itself, I would leave behind 1. And so there you go. We have just factored this trinomial here by factoring out 5c cubed out of each of the 3 terms. In honesty, ladies and gentlemen, if you've never done this ever before in your mathematical lifetime, you are in the wrong course. You should probably be in elementary algebra, Math 082 here at Mott Community College, and not Math 130. All right. Any questions about that one there? All right, let's try another one here. We got 4t times u plus 8v minus 3 times u plus 8v. Now, this looks a lot more different than the one we just got done doing, but nonetheless, it is a polynomial in the variable u and v and t, and we're being asked to factor it. So what can we do here? Well, hopefully we realize that between this term and this term, separated by subtraction, there is a common factor, and that common factor happens to be this binomial factor of u plus 8v. So since u plus 8v is a common factor with this term and this term, we can factor it out of both of these terms. So I can literally factor it out of both terms. Now, when I factor it out on the next line of my paper, I only represent it one time. Times, now what would I leave behind after factoring it out of both these terms? When I factor it out of the first term, I'll leave behind just 4t. When I factor it out of the second term, I'll leave behind just minus 3. And there you go, ladies and gentlemen. This would be the factorization of this polynomial. Hopefully that rings a bell that you've done that before or seen that, where you can factor a whole binomial factor out. That is legal to do that. Any questions about that one there? Now, when you factor a polynomial, you can always check your answer. All you got to do is just multiply things back out, and you should get back what you originally had. For instance, if I take this u plus 8v and multiply it by 4t, I get back 4t times u plus 8v. Minus, if I take u plus 8v times 3, I get back 3 times u plus 8v. If I took the 5c cubed and distributed it back into all three of these terms, I would get back what I originally had. That's how you can check your answer to make sure you're factoring correctly. All right, let's try this one here. We got 6ty plus 9y plus 14t plus 21. This is a 4-term polynomial, and we want to try to factor. First thing we should always ask ourselves is, can I factor anything out of all the terms of the polynomial other than 1 or -1? As you can always factor 1 or -1 out of any polynomial. Well, what do you think? Can I factor anything out of all 4 of these terms? Doesn't really look like it, does it? The only thing that divides into 6, 9, 14, and 21 would be 1 or -1. Can't factor a y out of all 4 terms, because although the first 2 terms have a y as a factor, the last terms don't have a y. Can't factor a t out because the second and the last terms don't have a t. Initially, it doesn't look like this thing's factorable. And some polynomials are not factorable. You cannot factor all polynomials. But, ladies and gentlemen, this is a 4-term polynomial. And when we have a 4-term polynomial, we should always try to use what's called the grouping method to see if it can factor. So I'm going to demonstrate the grouping technique or the grouping method. As the name suggests, we're going to be grouping things together, and we will group together our first 2 terms by placing them inside parentheses. Plus, and then I will group together my last 2 terms by placing them also inside parentheses. Now we put under the microscope the first 2 terms. What can I factor out of these first 2 terms here? Anybody? What can I factor out of 6ty and 9y?
3.
Yeah, you can factor a 3 out. Anything else?
A y.
3y.
And a y. Yep, you can factor 3y out of both these first 2 terms here. There it is, times, what would I leave behind in the wake of that? Well, 3y times what gives you back 6ty? That's going to have to be a 2t. Plus 3y times what gives me back 9y? That'd have to be a plus 3. Plus, now we shift our attention to the last 2 terms. What can I factor out of 14t and 21? I can factor out what out of both these terms here?
7.
A 7? I can factor out a 7. And when I factor out a 7, I leave behind what? 2t plus 3? 2t plus 3. Now, ladies and gentlemen, do we recognize something here? Both these terms share a common what? Binomial factor, which is what? 2t plus 3. So we can factor the 2t plus 3 out of both these terms times what do I leave behind? I'll leave behind 3y plus 7. And this is considered to be the factorization of this 4-term polynomial. There you go. And check your answer. If you were to multiply or FOIL this back out, 2t times y gives you back 6ty, 2t times 7, 14t, 3 times 3y, 9y, 3 times 7, 21. And we're done. Any questions? Hopefully this jogs your memory. Hopefully we've all at least seen the grouping method or have used it before in the past. That's called the grouping technique. All right, let's try to factor this one here. Now this is going to be CD minus 8D plus 4C minus 2D squared. To factor this 4-term polynomial, again, we will try grouping on it. as there's nothing I can factor out of all four terms. Out of the first two terms, I can factor a D, and that leaves behind C minus 8. In the last two terms, I can factor out a 2, and that leaves behind 2C minus D squared. But this don't look good. It don't look good because the binomial we leave behind, they are not duplicates of each other. So it doesn't look like we can go any further here. This appears to not be working here. The grouping method fails here. It's not working. So does that mean that this is non-factorable? Well, before we throw in the towel on this one, we might want to try one more thing. Maybe by rearranging some of these terms, ladies and gentlemen, we can force the grouping method to then become successful. So what I'm going to do is I'm going to flip these two terms around here, just rearrange them. So I got CD minus 4C minus 8D minus 2D squared. We still have the same four-term polynomial, nothing changes here. And now we will try grouping again here. Very careful when you got a minus sign preceding your third term and how you group your last two terms together. I like to leave the minus sign outside the parentheses, in which case I got to remember something. I got to remember to change the sign of my last term. So it must become a positive 2D squared. If you don't do the sign change, you'll have a sign error here, because this minus sign wants to redistribute back inside the parentheses, and you have to get back originally what you had was a minus 2D squared there. Okay. Now, what can I factor out of the first two terms? I can factor a C out, leaving behind D minus 4. Minus, in the last two terms, I can factor a 2 and also what? A D, leaving behind 4. 4. Wait a minute here. Yeah, I would leave behind 4 plus something's wrong. Hold on a second. Let me take a look here. What is going on here? Minus 2D squared. Minus 2D squared. So got minus this one. Oh, this should be C plus 4. This should be a plus here. I do apologize. There we go. All right. Sorry about that. Now we factor out 2D out of both these terms, and we have 4 plus D left over. But ladies and gentlemen, do I leave behind duplicate binomials? And the answer is yes. You know, 4 plus D is the same thing as D plus 4. And so therefore, I can now factor out the common binomial factor times what do I leave behind? C minus 2D, and we're done. This would be the complete successful factorization of that four-term polynomial. So look, at the bottom line is sometimes you may have to rearrange some of your terms in a four-termer in order to enable the grouping method to work. And that's a classic example. Okay. Any questions about that one there? All right. All right, so that's representing or illustrating the grouping technique on a four-term polynomial. All right, let's look at factoring a couple of trinomials now. How about factoring like W squared plus 5W minus 66? So how would we factor this trinomial? Notice it's a trinomial, one where the leading coefficient is positive 1. This is called the leading coefficient. This is called the middle coefficient. And this is called the constant term. Another thing of interest is to note that this trinomial is written in descending order. The degree of each term decreases from left to right. Second degree term, first degree term, 0 degree term. Another thing to note, ladies and gentlemen, is that this trinomial is said to be quadratic in form. Quadratic in form. What does it mean for a trinomial to be quadratic in form? Well, any trinomial whose leading degree is twice the middle degree is said to be quadratic in form. So if the leading degree is twice the degree of the middle term, your trinomial is quadratic in form. Now, if trinomials are factorable into the product of two binomials, they have to be quadratic in form. Is this trinomial quadratic in form? Is this degree twice the degree of the middle term? And the answer is yes. So if this trinomial factors, it will factor into the product of two binomials. Now, the question is, can it be factored? And how do we find those two binomial factors? Well, a method that is pushed in early algebra is the product sum method. The product we need to achieve is -66 here. And the sum we have to have is going to be the middle coefficient of +5. And so, ladies and gentlemen, the search is on to try to find a couple of factors of -66 that add up to a +5. And I would recommend you climb the ladder. Start with 1, try 2, try 3, try 4. That way you won't miss any. So -1 times 66. But these are no good because -1 plus 66 adds up to 65. And that's not even close to our 5 here. So we must continue the search. -2 and 33 are factors of -66, but these are no good because these sum up to 31. We need to have them sum up to 5. We got to continue to search. -3 and 22, but these aren't going to add up to 5. 4 does not divide evenly into 66. 5 doesn't. 6 does. -6 and 11. And notice -6 plus 11 do add up to what we need, namely +5, the middle coefficient. And so therefore we found the combination of factors of the constant term -66 that sum up to the middle coefficient of 5. Being the case, we can factor our trinomial. The first terms of our binomial factors have to be W, because W times W has to give you back W squared. And the last terms will be our decided upon factors here. So I can put like the -6 here and the +11 here. Or I could have these switched around. I could have the W plus 11 here times the W minus 6 here. At any rate, this trinomial factors completely into this. Any questions about how we factored this easy type of trinomial here with the leading coefficient of 1? Does that make sense there? Have you ever factored a trinomial like that before? If you never factored an easy type of trinomial like this, ladies and gentlemen, again, you could have the wrong course. All right. This is something that you initially see way back in elementary algebra, introductory algebra. All right. Any questions about that there? And of course, you could check your answer by multiplying this all out and collecting together and adding together your like terms, and you would end up with your trinomial back here. Okay. Now, how about the difficult trinomials? Okay, ladies and gentlemen, this is a difficult trinomial to factor because unlike the last one, the leading coefficient is no longer +1, it's +3. Factoring these types of trinomials is more challenging. Okay, it's not as simple as finding factors of the constant term that sum up to your middle coefficient because the leading coefficient now is in the way. There's two main ways to factor these types of trinomials. You can use a trial and error method, of which is just that. It's a bunch of trial and error trying to come up with trial factors that do indeed multiply together to give you this. Or there's a method that is, I would say, maybe slightly more popular because it minimizes the guessing. It's called the grouping method. And I am going to illustrate the grouping method just to jog your memory if you've used this in the past, or if you haven't. If you use the trial and error method, maybe you'll fall in love finally with the grouping method. The bottom line is, in all honesty, I don't care how you factor this trinomial. We just have to get it factored, okay? The grouping method works this way. You initiate the process by multiplying the leading coefficient in the constant term. So you take the 3 times the -20. 3 times -20 is going to be -60. And now the search is on. This is the only part of the process where the trial and error sets in. And we're just trying to find a couple of factors of -60 that sum up to -11. And you can start listing factors of -60, -1 and 60. But these are no good because these add up to 59. We need to have them sum up to -11. So the search continues. -2 and 30. And these are no good. These add up to 28. -3 and 20. And these are no good. These add up to 17. We're closing the gap though, but we still got to continue to search. -4 and 15, notice these add up to +11, but we need to have them sum up to -11. Tell you what, let's switch the signs. How about a +4 and a -15? These are factors of -60. that do indeed add up to what we need, namely -11. Okay. So ladies and gentlemen, we found our combination of factors that's going to enable us to factor this difficult type of trinomial. It's these right here. And now the beauty of this method is the guessing is all over. Now it's just all systematic from this point onward. I'm now going to rewrite my trinomial as an equivalent 4-term polynomial, where my middle term here is going to be split up and written as the sum of my decided upon factors. So this -11y is going to be written as plus 4y minus 15y. Or you could have these switched around. You could have the minus 15y plus 4y. It doesn't matter what order you list these. The factorization will come out the same. Now we have a 4-term polynomial, equivalent 4-term polynomial for a difficult trinomial. So how are we going to factor it? You guessed it. We're going to use the grouping method. So we group together our first 2 terms. Careful in grouping your last 2 terms together because I got a minus sign that precedes this 3rd term. So I must change the sign of my last term to avoid a sign mistake. What can I factor out of the first 2 terms? Factor out of y, leaving behind 3y plus 4. And what can I factor out of the last 2 terms? 5, leaving behind 3y plus 4. Everything's looking good here. We have a common binomial factor of 3y plus 4 that can now be factored out of both terms. There it is. Times, what do I leave behind in doing that? Y minus 5. Ladies and gentlemen, we're done. We have factored this difficult trinomial, and that would be its factorization. That's called the grouping method. If you want to factor these using trial and error, if you're used to that method, go with it. All right. I recommend that you pick a technique that you're most comfortable with and that consistently gives you correct factorizations. All right. Some of you do like the grouping method and have used it in the past. Go with it. Get good with it. If you like the trial and error method, use the trial and error method. Bottom line is that's factored. All right. Now this next one here is going to illustrate something that's going to be important with any polynomial. And that is to say, ladies and gentlemen, that we may have to undertake more than one step to get our polynomial completely factored. It happens all the time. So the first question again, we should always ask ourselves when we're staring at any sort of polynomial is, can I factor anything out of all the terms? What can I factor out of all 3 of these terms here? Anybody, what would be my greatest common factor?
5. 5u to the 2.
Okay, so we can factor a 5 out and also a u squared. You're correct. That would be the greatest common factor. And when I factor that out of all of my 3 terms, what am I going to leave behind? Well, 5u squared times, it looks like u squared would give me back 5u to the 4th minus 5u squared times, it looks like 8u would give me back my 40u cubed plus 5u squared times 7 would give me back my 35u squared. All right, so we got that factored like that. But we got to ask ourselves, is this completely factored? Well, ladies and gentlemen, we need to investigate this trinomial we leave behind inside the parentheses and ask ourselves, can it itself be further factored down? Because if it can, we need to do that. Fortunately, by having factored a 5u squared out of all 3 terms, we form a trinomial that has a nice leading coefficient of 1, and it happens to be quadratic in form, unlike the initial trinomial. So we ask ourselves, being an easy type of trinomial, where you do not have to use the grouping method on these easy types, all we need are 2 factors of 7 that add up to a -8. Can anybody think of 2 factors of positive 7 that sum up to -8?
-1 and -7.
All right, so -1 and -7, as it turns out, are the only factors of positive 7 that do indeed sum up or add up to our -8. Being the case, this trinomial now will immediately factor, oh, by the way, don't lose your 5u squared you initially factored out. That's part of your final factorization. But now I'm going to further factor down this trinomial now into u minus 1 times u minus 7. Or you could have this switched around. You could have the u minus 7 here and the u minus 1 here. Ladies and gentlemen, there it is. We're done. Bottom line is that is completely factored. And we are done with that problem. Does that make sense? Any questions about that one there? So yeah, just make sure in the future when it says factor, we will always assume that we have to completely factor polynomials. Make sure you can factor them all the way down as much as possible. All right, good on that? Okay. Now we're going to look at the binomial family. And I would recommend that you memorize all of these patterns here. Ladies, I'm just only going to help your cause, not only in this course, but if you go onwards into higher level math, it's wise to have these in your mind bank. Okay. The binomial family. If I have this type of binomial here, I have what is called the sum of squares, the sum of perfect squares. And you know what? The sum of perfect squares cannot be factored over real numbers. It can over imaginary complex numbers, but not over real. So we would say that this is non-factorable over real numbers. Or we would say that it's like a prime polynomial. Not all polynomials can be factored. Sometimes they're prime or they're non-factorable. Contrast that one with this one here. This is called the difference between squares. That's the difference between perfect squares. And unlike the sum of squares, the difference of squares can be factored. So this would factor into a plus b times a minus b. And any binomials that look like this and differ only by the sign in between the terms are called conjugate binomials. So these are conjugates of each other. Conjugates. All right, that's how you factor the difference between perfect squares. And then we run into the binomials that are the sum and difference of perfect cubes. This is called the sum of cubes. The sum of cubes can always be factored into the product of a binomial and a trinomial. Specifically, the sum of these cubes would factor into a plus b times a squared minus ab plus b squared. That's how this sum of cubes would factor. In a similar fashion, this would be the difference between perfect cubes. And the difference of cubes factors in a similar way that the sum of cubes factored. The only difference is that these signs switch. So this would factor into a minus b times a squared plus ab plus b squared. I would recommend that you memorize the binomial family and how they do or do not factor. I would just memorize all of these. Notice the sum and difference of cubes are very similar in their factorizations. The only difference is the sign here and here. I always remember it this way. If this is a plus sign, this sign is also plus. This is a minus, this is a minus. And these signs are always opposite. So plus, minus, minus, plus. Okay, so pretty easy to remember that there. That's your binomial family. All right, let's try out a couple here. Let's try to factor 16t squared minus 49. This is a binomial. We want to factor it. And notice, unfortunately, we cannot factor anything out of both these terms. And so we got to ask ourselves, what kind of a binomial do we have here? Anybody want to weigh in as to what type of binomial we have here? What kind of a binomial is this? Is it maybe the sum or difference of cubes, do you think? Or maybe the sum or difference of squares?
Difference of squares.
Okay. You know, on your calculator, you have a square root function. If you take the square root of 16, you'll discover you get a nice integer of 4. That means 16 is a perfect square of 4. You take the square root of 49, you get a nice whole number, which is 7. So 49 is perfect square of 7. Yeah, we do have the difference of squares. In fact, you could write it as 4t quantity squared minus 7 squared to clearly illustrate that you do have the difference between perfect squares here. Being the case, it must factor into the product of conjugate binomials like this. So think of it this way here. Put the pattern right below it so it helps you and guides you along here. That's why it's nice to remember these patterns here. My A is like a 4t and my B is like a 7. So my A gets replaced with 4t here and here. My B gets replaced with 7 here and here. So this factors into 4t plus 7 times 4t minus 7. And ladies and gentlemen, we're done. This would be the correct factorization of this binomial difference between two squares. That makes sense? Okay. So yeah, again, I would just throw these in the memory bank. It's going to help you not only in this course, but you get into calculus, ladies and gentlemen, you have to know how to factor polynomials also. So it just expedites things. Let's try another one. All right, let's try to factor 8v cubed minus 27. What kind of a binomial are we up against here? Well, might it be the difference between squares or cubes? Notice there's nothing we can factor out of both these terms either. So what do we got? Difference of cubes or squares? What do you think?
Cubes.
Yeah, there is a cubed root on your TI-83. It hangs out in your math menu. If you hit your math button, you'll see a cubed root function. You take the cubed root of 8, you'll discover 8 is a perfect cube of 2. The cubed root of 27 is 3. Okay. So yeah, definitely we do have the difference between perfect cubes here. And underneath it, I'm going to put the template, if you will, as to how we factor the difference of cubes to kind of guide me along. Now, you don't have to do this if you haven't memorized well enough. You don't need to do this, but you know, this would be how we factor the difference of cubes. My A is really a 2v and my B is really a 3. So A gets replaced throughout with 2v and B takes on the value of 3. So here we go. So this factors into A minus B, which is to say 2v minus 3 times 2v squared. What's 2v times 2v? That would be 4v squared plus A times B is to say 2v times 3. 2v times 3 is 6v plus B squared. B is 3, so what's 3 squared? 3 times 3 is 9, and there you go. This would be the factorization of that binomial being the difference between perfect cubes. That would be the correct factorization. So again, knowing these patterns can help you to factor various binomials here.
What?
What's that? Is there a question? Okay. Let's take a look at this next one here. How about u to the 4th power minus 81? What do I got going on with this one? It's a binomial. Is it the difference of squares or cubes? What do you think? Squares or cubes?
Squares.
Yes, u to the 4th power is really the square of u squared. Remember, when you raise a power to a power, you multiply the exponents. And 81 is a perfect square of 9. So you can clearly see we do have the difference between perfect squares. And so it has to be factored as the product of conjugate binomials. So therefore, this will factor into u squared plus 9 times u squared minus 9. Am I done? Is this completely factored, or can I further factor down any of these? Well, this appears to be the sum of squares, but we just discussed that the sum of squares cannot be factored over real numbers. We call this factored completely. But this, as it turns out, is also the difference between squares, 9 being a perfect square of 3. So this needs to be further factored down. We're not done here. So the complete factorization is going to have me further factor down this u squared minus 9 into u minus 3 times u plus 3. Now, ladies and gentlemen, this would be the complete factorization of this difference between perfect squares there. And we are finally done, because none of these remaining factors can themselves be further factored down. So that's the complete factorization there. All right. Is that making any sort of sense there at all? Okay.
I have a question.
Yeah, go ahead.
before we move on. So when you were asking, like, is it a difference between squares and like cubes? How do you tell the difference? I've never been good at that.
Okay. As far as like the variables are concerned, like u to the 4th power, you would ask yourself, does 3 or 2 divide into 4? Does 3 divide into 4 evenly?
No.
But 2 does, doesn't it? 2
Right.
does. And that's why u to the 4th is a perfect square of u squared. Okay. Now, as far as this number is concerned, you're welcome to get on your calculator and take the square root of 81. If it gives you a whole number, then that means 81 is a perfect square. Okay.
Okay.
If you take the square root of a number like 7 and you don't get a whole number, like, you get some sort of a decimal, like what is the square root of 7? Well, it's going to be somewhere between 2 and 3. Do you agree? Something between 2 and 3. So like if you take the square root of 7 here, what happened to my calculator? Okay. So if you take the square root of 7, you're going to have a decimal, which is going to be like 2.645, blah, blah, blah. Well, since you did not get a whole number, this is not a perfect square, correct? 7 is not a perfect square. Now, as far as cubes are concerned, if you had like u to the 6th power, well, I'll tell you what, let's try u to the 9th power. Is this a perfect square or a perfect cubed here? Well, to find out, you can ask yourself, does 2 divide into 9 evenly? No, so this is not a perfect square, but does 3 divide into 9 evenly?
Yeah.
Yeah, so this would be a perfect cubed of what? Of u cubed. Okay. You see
Okay.
that there? And as far as like the numbers are concerned, like if you had like trying to think here, if you had see like 27, is 27 a perfect square or perfect cubed? Well, you could try to take the square root of 27 and see if you get a whole number, but unfortunately when you take the square root of 27, you get like a messy decimal, like 5.19615, blah blah blah. So that's not a perfect square.
Okay.
But if you take the cubed root of 27, you'll discover you get 3. You see that?
Yeah.
That's an
Okay.
indication that this is a perfect cube, okay, not a perfect square. All right.
Okay. Thank you.
Does that help out a little bit there?
Yeah. Thank you.
All right. Now, so yeah, you're welcome to use your square root function on your calculator and also your cube root function to determine like if a number qualifies as being a perfect square or cubed. And just remember, for the variables, just try to divide 2 into the exponent. If 2 divides evenly into it, then it's a perfect square. If 2 does not divide evenly into the exponent, but 3 does, then it's a perfect cubed. All right, now this problem here gives us yet a different look as to what a polynomial could look like. And we're being asked to factor this here. Now, one way to do this problem, and a long, difficult way to do this problem, is to multiply this by itself, distribute the -3 inside here, and then combine like terms, and then try to factor it from there. Ladies and gentlemen, there's a much easier way to do this as opposed to that. An easier way to do this is to get back and look at the forest for the trees. Do you agree that I got x squared minus 2 here that's being squared, and I have x squared minus 2 here that's being raised to the 1st power? In an overall sense, we have a quadratic form trinomial because the power of the leading term, which is 2, is twice the power of the middle term, which is 1. Furthermore, to help us see the forest for the trees, it's wise in this case to use what's called a U substitution. And U substitutions are used all the time in calculus to help simplify complicated situations, enabling us to see the forest for the trees so that we know what to do. A U substitution would be the way to go here. I would want to let U be equal to x squared minus 2. So I would let U be equal to x squared minus 2, in which case U squared then would have to be x squared minus 2 squared. Isn't that true? Being the case, I can basically transform this polynomial into the variable U. I can rewrite my trinomial now as U squared minus 3 times U minus 28. Everybody understand what I just did here? With the understanding that U is this. Okay, isn't that true? If U is equal to this, doesn't this polynomial become this in U? Now it's easier to see what we need to do. Notice it's an easy type of trinomial to factor in the variable U. All I need are a couple of factors of negative 28 that sum up to my middle coefficient of negative 3. And after some thought, hopefully you come across negative 7 and 4 as being the only factors of negative 28 that add up to negative 3. Being the case, this trinomial in U factors immediately into U minus 7 times U plus 4. But ladies and gentlemen, we got to just back substitute in the end and bring back what U was set equal to. So we just replace U now in our factored form with x squared minus 2. So this x squared minus 2 is going to drop in here, and it will drop in here. So our factorization is going to be x squared minus 2 minus 7 times x squared minus 2 plus 4. And now finally cleaning these up, we would have x squared minus 9 times x squared plus 2. Am I done, or can I further factor down any of these remaining factors now? Well, notice this turns out to be the difference of squares. So it itself needs to be further factored down because 9 is a perfect square of 3. If you take the square root of 3, you get, excuse me, you take the square root of 9, you get 3. So this itself further factors down into x minus 3 times x plus 3. This cannot be further factored down, even if it was the sum of squares, which it is not, because 2 is not a perfect square. It couldn't be factored anyway. So whatever, we just bring it down. We're finally done. This is done. So therefore, this has been successfully completely factored. And we utilized a U substitution to help us do that, to see the forest for the trees. So that's an invaluable situation there where a U substitution is mighty handy. Okay. And U substitutions are used all the time in calculus to help us, again, simplify things so that we can see the forest for the trees, so to speak, so that we know exactly where to go with the problem. So get used to U substitutions if you go into calculus. Any questions about that problem there? Okay. Oh, thank you for that comment. Somebody indicated they never used the U substitution method before, but you know, you got to admit, once making the U substitution, this very difficult polynomial here, a very messy polynomial, becomes trivialized. Isn't that amazing? And that's the purpose of a U substitution, to take something very complicated and to trivialize it, make it so simple looking. That's its intention. So you got to love the U substitution. They are amazing. And they also are used, like I said, in higher level math to help you deal with very complicated situations rather easily. All right, another thing, ladies and gentlemen, we are going to run into maybe having to factor out some negative exponents out of terms. It happens all the time, and a classic example would be in calculus. Oftentimes, you're having to factor out terms that have negative exponents. So we're going to try to factor this construct here. And to do so, of course, we're going to have to try to factor out the greatest common factor out of all 3 of these terms. And let's just look at the coefficients first. What would be the greatest common divisor or factor of 5, 2, and 1? Well, that's only going to be 1 or negative 1, correct? So there's really nothing we can factor out of 1, 2, and 5. Let's look at the variables. What can I factor out of t to the negative 7, t to the negative 6, and t to the negative 5? Well, keep in mind, when we were factoring greatest common factors out of each term of a polynomial, we always factored the smallest exponent out. So what would be the smallest exponent? Would it be t to the negative 7, t to the negative 6, or t to the negative 5 power? What would be the smallest exponent? Anybody?
The negative 7 one.
That's right. So we got to factor out t to the negative 7 out of each of these three terms because this is the smallest of the three exponents. So here we go. There's our, what we call our greatest common factor, going to be factored out of all three terms. And the question is, what do we leave behind? Well, when you factor out t to the negative 7 out of 5 times t to the negative 7, it's pretty easy to see here that you'll leave behind just 5. But it's not so easy to see what you leave behind when you factor t to the negative 7 out of 2t to the negative 6. To help us, here's what I recommend you do. Take the t to the negative 6 off to the side of your paper, place it over what you factored out of it, which is t to the negative 7, and now simplify or reduce this, and you'll understand what you leave behind. When we divide like bases, we are taught to subtract exponents. So this is really t to the negative 6 subtract negative 7 power, which is really going to be t to the negative 6 plus 7, which is really t to the first power. So when you factor t to the negative 7 out of t to the negative 6, you leave behind t to the first power. So we're going to leave behind 2t to the first power. Minus, what do I leave behind when I factor t to the negative 7 out of t to the negative 5 power? Well, again, feel free to take the t to the negative 5 power off the side of your paper, place it over t to the negative 7, and now reduce. This reduces down to t to the negative 5, subtract negative 7. And hence we're left with t to the negative 5 plus 7. And heck, we leave behind t to the second power when we factor t to the negative 7 out of t to the negative 5. So this is t to the second power. And there you go. Everybody understand what just happened there? All right, now it's awkward to leave a negative exponent appearing in a final answer. We are always taught to not to do so unless we're working with scientific notation. So being the case, ladies and gentlemen, because of definition of negative exponent, what do I mean by definition of negative exponent? That means when you got something raised to a negative exponent, to do away with the negative sign on the exponent, we have to take the base and flip it from where it's at. So this x would have to be flipped down into the denominator, and I would have my equivalent expression, which is 1 over x to the positive n power. This is the definition of negative exponent. Or if I have my negative exponent appearing in the denominator, I would flip the base x up into the numerator and call it x to the positive nth power over 1. All right. So the bottom line is I got to get rid of this negative exponent on t. To do that, this t's got to be reciprocated or flipped down into the denominator, in which case I would have 5 plus 2t minus t squared, and that's all going to sit over t to the positive 7th power then. Another thing we have to maybe consider is, can we further factor this trinomial here? This trinomial is all out of sorts, if you will, because it's not written in descending order. Feel free to rearrange these terms to get this in descending order. No problem. You can easily do that. Now it's in descending order. Another thing that I don't like is my leading coefficient is a negative 1. We would like it to be positive 1 because then it would be an easy type of trinomial to factor. We can arrange for that to happen too. All I got to do is factor a negative 1 out of all three of these terms. You can always factor a negative 1 out of any polynomial. The effect it has on the terms is just to toggle the signs. And now we just ask ourselves, just to be safe about things, can I further factor this trinomial? Notice it's an easy type now, one with a leading coefficient of 1. Are there two factors of negative 5 that sum up to negative 2? The answer is no, because the only factors of negative 5 are negative 1 and 5, or 1 and negative 5, but none of those add up to negative 2. So, you know what? You could go back here, leave your answer like this if you want. Or, ladies and gentlemen, you could even leave your answer like this. Or you can leave your answer like this. They're all equivalent. You can even bring this negative 1 factor outside of the fraction. And you can cite your final answer like this. All of these are equivalent. This is equal to this, which is equal to this. I would take either one of these as being an answer, and we're done. Okay. Any questions about this here? All right, I know this sounds like a lot, and I haven't given you any classworks yet because I burned a lot of time going over the schedule and the syllabus, and that's why I don't like first days. It consumes a lot of valuable class time. So don't worry if you don't get a classwork today. I mean, it's not your fault. We don't have one. We don't have one. All right. But I really want to try to cover as much as I can in the time remaining. I know this seems like a laborious, grueling lecture. Ladies and gentlemen, in the future, I will, interject classworks to kind of break up the monotony a little bit, but please forgive me for this lecture here. So we got this here. I want to show you how to factor a situation where we might have rational exponents that creep into the picture. If you get into your calculus, usually the first semester of calculus, oftentimes to simplify your final answer after performing integration or differentiation, whatever the case might be, you oftentimes have to factor out a rational exponent. It happens all the time. So, ladies and gentlemen, notice we can see that we do have a common factor that's shared by each of these terms separated by addition. It's for 3x plus 1. So what would be the smallest exponent on 3x plus 1? 2/3 or 5/3? Well, which one would be the case? So I can factor 3x plus 1 to what power out of both these terms here? What's the smallest exponent?
5/3.
We want the smallest exponent between 2/3 and 5/3.
2/3 then.
I will go with 2/3. So we can factor out 3x plus 1 to the 2/3 power out of both these terms here. There it is, times what would I leave behind? Well, when you factor it out of the first term, which is 5x times 3x plus 1 to the 2/3 power, you'll leave behind 5x. When you factor it out of the second term, it's not so obvious. And to help us understand what we leave behind, take the 3x plus 1 to the 5/3 power off to the side of your paper, place it over the 3x plus 1 to the 2/3 power, and now reduce. When we divide like bases, we subtract exponents. So this is going to leave behind 3x plus 1 to the 5/3 minus 2/3 power. Remember, we subtract exponents when we divide like bases. So this is going to be 3x plus 1 to the 3/3 power. But what's another name for 3/3? That's the first power. That's what we leave behind. So we're going to leave behind 3x plus 1 to the first power when you factor 3x plus 1 to the 2/3 out of 3x plus 1 to the 5/3. Last thing we could do is just simplify our second expression by combining like terms. 5x plus 3x is 8x plus 1, and we are done. And that's your answer. That's completely factored. All right, makes sense how we did that? All right, so that essentially is what I wanted to go over in section R5. And now R6, I will try to get through as much as I can in the remaining time. I did not finish R6 in its entirety with my face-to-face section this morning. And because of that, I told them I would probably have to make a little supplemental video, and then I'll attach it to Canvas for you to view to wrap up the rest of section R6 in your spare time, because I don't want to get off track of what I need to cover for the semester. We're on pretty much a very tight schedule as to what we need to cover according to what the college wants us to get through. All right, so ladies and gentlemen, we're now going to turn our attention to R6, which is entitled Rational Expressions. And radical operations. All right, first of all, what's a rational expression? A rational expression is any expression where you have a polynomial over a polynomial. So here's an example of a rational expression in mathematics, because we have a polynomial over a polynomial. In particular, we have a monomial over a binomial. This is collectively called a rational expression. For purposes, when we get into solving rational equations, oftentimes we're very concerned when the denominator of a rational expression becomes 0. Why are we concerned when the denominator becomes 0? Because what's anything divided by 0? Anybody? What's anything divided by 0? It's always considered to be what?
Unsoluble.
Yeah, or we say undefined. Yeah, you can never divide anything by zero in mathematics. It has no definition. And this is something that even computer programmers have to guard against when they're writing code to make sure that there is never a division by zero that is undertaken when the code is executed. It can cause your computer to hang up. All right, so ladies and gentlemen, we're very concerned here. I got to make sure that this denominator is never equal to zero. So I would like to try to find out for what values of x this would become zero. To do that, let's take the denominator and set it equal to zero. And now let's solve this equation. This is called a quadratic or second degree equation, and we're going to try to solve it for its two solutions. The easiest way to solve this quadratic or second degree equation is to use the factoring method. So what I'm going to try to do is completely factor the left side of this equation. What kind of a binomial do I have here? It's the difference of what? Not cubes, but the difference of squares. Yeah, because 49 is a perfect square of 7. Take the square root of 49, you get 7. And 2 is a perfect square, not a perfect cube. So therefore, this would factor in x minus 7 times x plus 7. Now, there's a theorem that says when you multiply two or more factors together and you get a product of 0, that means that one and or more of your factors have to be equal to 0. So by that theorem, I am justified in setting these factors equal to 0 and solving the subsequent first degree equations. When I solve for x here, I get x equals 7. When I solve this simple equation for x, I get x equals negative 7. And so, ladies and gentlemen, this rational expression gets into trouble if x is ever equal to positive 7 or negative 7. If that's the case, the denominator goes to 0. The rational expression is undefined. So therefore, we would say the domain of this rational expression, the domain would consist of all real numbers x such that x can never be equal to positive or negative 7. That would be a way of representing the domain of this rational expression. Again, the domain represented using set builder notation or set notation is saying the set of all real numbers x such that x can never be equal to positive or negative 7. Another way to represent this domain, or all real numbers that are not 7 or negative 7, is to use what is called interval notation. Interval notation is used a lot in calculus. Interval notation makes use of parentheses and or brackets. So to represent all real numbers that are not equal to positive or negative 7, here's how I would do this using interval notation. Envision that I work on the number line from left to right. Here's negative 7, here's positive 7. From left to right. To left forever is negative infinity. So not including negative infinity. And by the way, negative or positive infinity, you never include because they're not numbers. They're just concepts of moving in a direction forever. So not including negative infinity, comma, up to negative 7, but we do not include negative 7. So I don't put a closed bracket next to negative 7 because negative 7 cannot be in this set. So I have a closed parenthesis. In union with, the union operation joins sets together in union with, not including negative 7, comma, up to positive 7, but not including 7, hence closed parenthesis, in union with, not including 7, up to positive infinity, and then a closed parenthesis. This would be the formal interval notational way of representing the domain of this rational expression, which is a set of all real numbers except 7 and negative 7. Okay, that's called interval notation. This becomes more important. These restrictions on the domain of a rational expression become extremely important when we start solving rational equations, of which we're not going to do today. We don't have enough time. We'll get to that a little later on. Okay, any questions about that there? All right, so what are we going to do with rational expressions here to wrap up this session today? Well, first of all, ladies and gentlemen, let's try to reduce some rational expressions. As we always try to reduce fractions, so too, we always try to reduce rational expressions in general. Suppose I have this rational expression here, and I am asked to reduce this rational expression. How can I do that? Well, one thing you cannot do, and please do not do this, this is called illegal algebra. You cannot reduce the x squareds out. You can't cancel these x squareds out. I know it looks very tempting to want to do so, but you cannot do that. And the reason why you cannot do that is because separating these terms is not multiplication, but subtraction. And separating these terms is not multiplication, but subtractions. You cannot drop the x squareds out. No, what we need to do first is we got to completely factor our numerator and our denominator. And so we have to factor our polynomials. How would I factor x squared minus 9? Well, after some thought, hopefully you realize it's the difference between perfect squares. So it would factor in x plus 3 times x minus 3. That one's done. How can we factor the denominator? Well, the denominator is an easy type of trinomial, one with a leading coefficient of 1. Being the case, all I need are two factors of negative 21 to sum up to negative 4. And after some thought, it would be negative 7 and 3 as the only factors that work that do add up to negative 4. Being the case, this trinomial factors immediately in x minus 7 times x plus 3. And now that we completely factored the top and bottom, we ask ourselves, can I cancel out any like factors between the numerator and denominator? So, ladies and gentlemen, what can I factor out? Or excuse me, what can I reduce out between the numerator and denominator here? I can reduce the what's?
X
X
plus
plus 3.
Yeah, the x plus 3 divides into itself once, divides down here, and the x plus 3 one time. When you cancel like factors out between the numerator and denominator, don't forget to put ones because you leave factors of ones behind. So our final answer is 1 times x minus 3, which is this x minus 3 over x minus 7 times 1, which is x minus 7. And that's your answer. We're done. We've reduced this rational expression. Don't cancel these x's out at the end. That's illegal. You can't do that because separating these terms is not multiplication, but additions or subtractions. That's why you cannot drop these out. That's it for that one. All right, do you remember how to divide rational expressions? If I have like x cubed minus 64 divided by 16x squared, minus x cubed, and I want to divide that by, let's say, like 2x squared plus 8x plus 12, and this sits over x squared plus 2x minus 8. It's our job to divide these rational expressions. Well, think back with basic math. In basic math, when we divide or multiply fractions together, we do not need a common denominator. And specifically when we do divide fractions, do you remember how we divided fractions back in basic math? We changed division to multiplication and flipped the second fraction upside down. In general, we were taught this many years ago. Okay, same thing here. We're going to change division to multiplication, and then we're going to flip the second rational expression upside down. Try not to forget this. If you forget to reciprocate the second rational expression, that will be an error. And now, ladies and gentlemen, before we can do any sort of cross canceling or reducing, we have to first of all completely factor all of our polynomials. So how can we factor x cubed minus 64? Well, this happens to be the difference between perfect what? Squares or cubes? What do you think?
Squares
Okay, you're saying the difference between squares.
or cubes, my bad.
Not squares, because 2 does not divide evenly into 3, but 3 divides into 3. So it looks like this might have to be the difference of cubes. I have another question. What's the cube root of 64?
4.
Yeah, 64 is a perfect cube of 4. Okay, so yeah, we do have the difference between two cubes here, and so it must factor. And it would factor according to, remember that pattern there, back there? This factors into a minus b times a squared plus ab plus b squared. That's how you factor the difference between cubes. And again, just try to memorize those patterns there for the binomial family. So you know what? Our a is really like an x, and our b is really like a 4, because 4 cubed is 64. So we just follow the pattern. So it's going to be a minus b, which is to say x minus 4, times x squared, plus x times 4, which is to say plus 4x. And then we have plus 4 squared at the end, which is plus 16. Downstairs, what can I do with this one here? And you know what? So that we don't have to keep rewriting our fractions over and over again as we strive to factor all of our polynomials, consider picking the polynomial up, taking it off to the side of your paper, and then completely factoring it off to the side. Then in the end, you can bring the factorization back and replace it back in your main problem. What can I factor out of both these terms here? I can factor an x out, and I'll leave behind 16 minus x squared. Now what I can do is hopefully realize that this is the difference between two squares. So this binomial needs to factor into the product of conjugate binomials, namely 4 minus x times 4 plus x, because this is the difference of two squares. 16 is a perfect square of 4, x squared is a perfect square of x. This would be the complete factorization of this denominator here. So let's bring it back and replace this denominator with its completely factored form. Now that's been completely factored. Times, now how can we factor this one here? Well, this is an easy type of trinomial to factor. I don't think I'm gonna have to drag this off to the side of my paper to factor it. I think I can find two factors of -8 rather, that sum up to +2. And those factors would have to be a +4 and what, a -2? So 4 and -2 are factors of -8 that add up to +2. So this trinomial here can factor immediately into x plus 4 times x minus 2. In the denominator, this does not appear to be an easy type of trinomial to factor. Being the case, I might want to drag this one off to the side of my paper and wrestle with it. When I get done, I'll bring back its factored form. So here we go. We're going to take this off to the side of our paper. And I realize that I can factor a 2 out of all three terms first. Let's do that first. And now I ask myself, can this trinomial itself be further factored down? Being an easy type, all I need are two factors of 6 that add up to 4. You know, the only factors of 6 are 1 and 6 and 2 and 3, but none of these sum up to 4. So it doesn't look like we could further factor this trinomial down. This would be the complete factorization of this denominator. Let's bring it back to the main problem now and replace the denominator with its factored form. All right, now that everything's completely factored, we ask ourselves, can we do any cross canceling or cross reducing this away, or can we do any reducing between the top and bottom here and top and bottom here? Anybody? What can we do? Any canceling?
X minus 4.
Yeah, now I'm glad you brought that up, because x minus 4 looks very similar to 4 minus x, but why are they not the same presently?
Because they're flipped around.
Yeah, the negative sign's in the wrong place. Do you agree? Here it's in front of the x, here it's in front of the 4. But look at, I'm going to show you something very important that we can do between these two factors. And I'm going to demonstrate that right here. So ladies and gentlemen, let's analyze quickly x minus 4 over 4 minus x. They look like they're the same, but they're not the same because the negative sign's in different places between them, but they do have the same terms, don't get me wrong. Now, here's what we can do. You can always factor a -1 out of any polynomial. This is the time and place to do such a thing. I could decide to factor a -1 out of the numerator or the denominator. Not both, but just pick one. I'm going to choose the numerator. I'm going to factor a -1 out of both terms in the numerator. When I do that, I'm going to leave behind -x plus 4. Isn't that true? When I factor -1 out of these terms, I'll leave behind this. Isn't that true? Now the denominator is 4 minus x. But wait a minute. Something looks familiar now. In fact, it looks like this -x plus 4. If I spin these terms around, I will now have 4 minus x. Well, that's the same as the 4 minus x in my denominator. And what happens to my 4 minus x's? They reduce out. So you know what this reduces down to? -1. So x minus 4 divided by 4 minus x reduces down to -1. -1. And I'll be honest with you, ladies and gentlemen, anytime you have any sort of structure like this, when you have a binomial of the form like a minus b over like b minus a, you don't have to go through this song and dance again. You can just reduce this down immediately down to -1. That's always the case. See that there? Shortcut. Anytime you have this, always reduces down to -1. So this reduces down to -1 for reasons of which I've demonstrated. So therefore, let's come back to our main problem. So therefore, this x minus 4, you are correct, will reduce with the 4 minus x. But in reducing out, it leaves behind a factor of not positive 1, but you leave behind a factor of negative 1. You have to acknowledge that by putting a factor of negative 1 somewhere. So I will do that. Notice this does not reduce out with anything down here or does not cross cancel out. And so we have to just pencil it back in. It's part of our final simplified quotient here. Now, anything else that we can reduce out or cross cancel out or anything? Look at the 4 plus x is the same thing as x plus 4. These reduce out, leaving behind factors of 1. Those are gone. And you know what? I can't see anything else. This x cannot cross cancel it out with anything here. It doesn't reduce with anything up here. This x minus 2 does not reduce with anything here. And this 2 cannot cross cancel out or reduce. So what do we got left? We got this trinomial times that negative 1 I mentioned because of this. We still got the x minus 2 that hangs around. Downstairs, I got 2x times this trinomial here, which is x squared plus 4x plus 6. As nasty as it looks, ladies and gentlemen, this is all we can do with this. Just leave it like this. Don't multiply all this back out. Just leave it like this, and we're done. We have divided these rational expressions. That's our final answer. Okay, and you know this negative 1 factor here? When you have a negative fraction, I don't know if you've ever seen this before. It doesn't matter where you attach the negative sign, whether you attach it to the numerator or the denominator, or just take it outside the fraction. These are all equivalent to each other. So my point is here, this negative 1 factor, you could just bring it outside your fraction. Just put it outside there. And then you would have this here. Okay, x minus 2. And this would all sit over 2x times x squared plus 4x plus 6. So feel free to bring this negative 1 factor outside. Just put it outside the fraction. Still equal. It's still equal to this. All
The
right.
denominator,
Yes.
is it 2x or is it 2? Because in the step before, it's just
Wait
2.
a minute. No, okay, I have my x here. You see that x there? I did bring the x down here. So yeah, it's still got to be the
Okay.
2x here, and then you got that trinomial here. So
I missed that.
yeah, it's there. Any other questions about that problem there? All right, we only have time for one more thing here, and then we got to wrap it up. Like I said, the schedule and the syllabus is killed all our time here. And for that reason, unfortunately, I'm not really able to, give you a classwork of which I really wish I could do so, but I just don't have the time for that. But expect those in the future, as we will not have this time crunch in the future here. I want to look at maybe adding or subtracting rational expressions. Well, go back in your thoughts to basic math. When you're adding or subtracting fractions, of course, you always need a common denominator. And the good news here is twofold. Number one, all my denominators are completely factored already. Number two, they happen to be common denominators. So life is good here. We already have a common denominator. So all we have to do now is just kind of like add our numerators. Notice we can't actually add these together. They're not like terms, but we acknowledge that we're adding them together by putting plus signs between the terms. And this all sits over our common denominator. But before you call it quits and throw in the towel, you need to ask yourself here, can I factor this trinomial in the numerator? Because if you can, it might lead to reduction. And that's something that will be expected of us. So we need to entertain this. Hey, lucky are we? Easy type of trinomial. All I need are 2 factors of 9 to sum up to 6. And they would be 3 and 3. So this trinomial in the numerator factors into m plus 3 times m plus 3. Being the case, look at it was important to factor that numerator because we can reduce now. This m plus 3 reduces out with one of these up here. Final answer is m plus 3, and we're done. That would be the simplified sum of these two rational expressions. Make sense there? Done with that one? All right, let's try another one here. Instead of saying add or subtract, your instructions could say just simplify. So like if the instructions here, instead of saying subtract, if it said simplify, we should know that we're going to have to subtract these rational expressions because we're staring at it. That's what it's saying. Can we subtract these rational expressions? Well, we need a common denominator. Unfortunately, we don't have a common denominator. Secondly, unfortunately, these are not factored. To put together a common denominator, first of all, we have to completely factor our denominators. So here we are with our factorization skills again. I can factor an x out of both these terms here. And this denominator, notice, is the difference between perfect squares. So it factors into x plus y times x minus y. Now that our denominators are completely factored, ladies and gentlemen, it's very easy to put together our required least common denominator. To be divisible by all these denominators, okay, how about to be divisible by this first denominator? We're going to need to have a factor of x in our least common denominator. And we're also going to need the binomial factor of x plus y. But this LCD has to be divisible by the second denominator also. Now, we already accounted for the x plus y, but we need a factor of what? X minus y. You are looking at your least common denominator of both these denominators. It must consist of these three factors. The next step now is to build these fractions up into equivalent fractions. Okay. And if we look at our first rational expression, its denominator has the x. We got the x plus y. We're missing the x minus y. Because of that, our first rational expression, top and bottom, has to get multiplied by x minus y. The second rational expression's got the x plus y. It's got the x minus y. It's missing the x. So the second rational expression, top and bottom, must get multiplied by x to build it up into an equivalent fraction or rational expression that now possesses the least common denominator. Now that we have a common denominator all the way across, we can combine our numerators. So we have x minus y minus the 2x, and this all sits over, you guessed it, our common denominator. Combining like terms in the numerator, we got 1x minus 2x combined to give you negative x. And this sits over, again, our common denominator. Our common denominator. One last thing is to investigate the numerator to see if it can be factored, because if it can, it might lead to reduction. Well, guess what? We could factor a negative 1 out of both these terms. And when I do that, I leave behind x plus y. Now, was that important to have done that? The answer is absolutely yes, because now we can see that the x plus y's need to reduce out. So this x plus y divides in itself, divides in this one down here one time. Final answer will be negative 1 over x times x minus y. We're finally done. We have successfully subtracted these rational expressions, and we're done. Well, ladies and gentlemen, unfortunately, that's about all the time I have left. I've worn out my welcome here. I will make a separate little video involving working with radicals, and I will attach a link to Canvas so that you can view it at your leisure. Hopefully this has jogged your memory a little bit and brought back hopefully good memories from your past mathematical experiences. And I will eventually open up a section quiz on chapter R on Alex to get you guys going. I will also open up some homework, the homework assignment, which will give you practice out of doing problems out of sections R1, R2, 3, 4, 5, and 6. I strongly recommend that you do the homework first on Alex before you attempt the quizzes. Always do the homework first, then the quizzes, and then the exam in that order. That way you'll maximize your probability of getting the highest grade in doing things. All right, any other questions or comments? I'll be on the line for a couple minutes. If not, you have a great, safe weekend, and hopefully I'll see you next week. All right, take care.
Have a good one. Mr. Ostermeyer.
Yes, go ahead.
I have a question about the Alex. I tried to